It's pouring outside. You sprint down the stairs of a subway station to escape the rain. The street above is turning into a river. Cars are parting traffic like boats. Storm drains are overwhelmed and water is starting to sheet across the sidewalks. You make it to the platform, soaking wet, and look around. The tile floor is dry. The tracks are dry. A train rolls in on schedule, and somewhere far above you, an entire city's worth of rainwater is hammering down on top of a tunnel that's 30 feet underground. So here's the question nobody really stops to ask. Why doesn't the water just pour in? Where does it actually go? And how is it that one of the most rain-vulnerable structures ever built by humans, a giant box buried beneath one of the wettest cities on Earth, almost never floods? The answer involves 700 pumps that never stop running, a flooded subway entrance from 2012 that became a national disaster, and a fabric so watertight it was originally developed for NASA spacesuits. Here's the first thing most people get wrong. They think subways have a rain problem. They don't. They have a water problem, and the rain has very little to do with it. The New York City subway pumps roughly 13 to 14 million gallons of water out of its tunnels every single day, even when not a single drop of rain has fallen on the city. That's the equivalent of about 20 Olympic swimming pools every 24 hours on a sunny day in July. The water comes from groundwater seeping through old tunnel walls, from leaking water mains overhead, from condensation, from spilled drinks, from the sweat of millions of passengers, and from 100 other sources you'd never think about. The city sits on top of an enormous, slow, constant flow of water that wants to go down. The subway just happens to be in its way. To handle this, the system runs roughly 700 dedicated pumps spread across 289 pump rooms throughout the network. They sit in low spots beneath the tracks called sumps, basically engineered low points where water naturally collects. Each pump uses a pressure sensor to detect rising water. When the water gets high enough, the pump kicks on automatically and pushes that water up through pipes that connect to the city's regular sewer system. The water travels from beneath your feet at the platform, up through pipes hidden in the walls, out into a sewer line, and eventually into the East River or the Atlantic. This system runs 24 hours a day. It has been running somewhere in the New York subway since 1904. It is, in a real sense, the only reason any of this works at all. Now here's the part that should genuinely surprise you. The subway is designed to handle a specific amount of rain falling on the city. The MTA's drainage system, including those 700 pumps, can collectively process about 1.5 to 1.75 inches of rain per hour. That's a very heavy storm. Most rainstorms, even ones you'd describe as torrential, are below that number. The pumps absorb the surge, push it out, and the platform stays dry. But when rain falls faster than 1.75 inches per hour, the system starts losing the race. The streets above flood first because the city's regular sewers can't keep up. Then water cascades down through the thousands of openings into the subway, and the pumps start drowning under more water than they can move. Quick favor before we keep going. If you've ever wondered about the engineering hiding in the cities you walk through, hit that subscribe button. We dig into the systems quietly keeping things working that you've never had to think about. Now, back to the subway. The thousands of openings are the real problem. The New York subway alone has approximately 40,000 sidewalk grates feeding air down into the tunnels. Add to that hundreds of street stairways, manhole covers, ventilation shafts, weep holes designed to drain water from behind retaining walls, and emergency exits. Every one of those openings is a place where water can get in. On a normal rainy day, a small amount of water enters through these openings, runs down to the tracks, and gets pumped out before anyone notices. On an extreme rainfall day, those same openings turn into waterfalls. That's exactly what happened on the night of October 29, 2012. Hurricane Sandy hit New York with a storm surge that peaked at 13.88 feet at Battery Park. Subway floods become possible when surge exceeds about 10.5 feet. Sandy was 30% over that threshold. Seawater poured into the system through entrances, vents, manholes, and tunnel portals faster than any pump could handle. 7 tunnels under the East River filled completely. The brand-new South Ferry Station in Lower Manhattan, which had opened only 3 years earlier and cost more than $500 million to build, took on roughly 15 million gallons of salt water. The Coney Island train yard in Brooklyn took on 27 million gallons. The MTA called it the worst disaster in the system's then 108-year history. Total damage was over $4.5 billion. The subway was closed for days. Some lines didn't reopen for years. The brutal lesson from Sandy wasn't that the pumps failed. The pumps worked. They just couldn't compete with millions of gallons of salt water pouring through openings that had been designed in 1904, when nobody was thinking about hurricane storm surges. So in the years after Sandy, the MTA started doing something remarkable. They went looking for technology that didn't really exist yet. Working with a New Jersey company called ILC Dover, the same company that builds NASA spacesuits and Mars rover airbags, they developed something called the FlexGate. It's a sheet of high-strength fabric made from materials similar to those in spacesuits that can be unrolled from a housing built into the top of a subway entrance, like a giant garage door. Once deployed, it forms a watertight seal across the stairwell. It can hold back floodwater up to 16 feet deep. The MTA has installed dozens of them at the most flood-prone stations in Lower Manhattan and parts of Brooklyn. That's not the only weapon. The MTA also commissioned something called the Resilient Tunnel Plug. This is essentially a giant inflatable balloon, 32 feet long, designed to expand inside a subway tunnel and seal it off completely, like inflating an enormous airbag inside a hollow log. It's deployed only as a last resort, but it can stop millions of gallons of water from advancing through a tunnel. The MTA has also installed thousands of portable vent covers, watertight manhole lids, and submarine-style steel doors at critical underground rooms holding electrical equipment. The South Ferry Station was rebuilt with deployable fiberglass covers built into the staircases, and key electrical systems were moved to higher elevations. In total, the MTA has spent more than $4 billion in federal disaster funds turning the New York subway into one of the most flood-resistant transit systems in the world. The work is still going on more than a decade after Sandy. Here's the part that should genuinely surprise you. Almost every underground space you've ever walked into uses some version of this same playbook. Constant pumping plus emergency barriers. The Tokyo Metro, one of the largest subway systems in the world, sits in a city built on soft, water-rich soil and faces typhoons every year. It runs continuous pumping plus a massive underground stormwater catchment system called the Metropolitan Area Outer Underground Discharge Channel, basically a cathedral-sized tank that absorbs rainwater before it ever reaches the trains. The Paris Metro, opened in 1900, deals with the constant pressure of the Seine. Pumping never stops. The Holland Tunnel and the Lincoln Tunnel, which carry cars under the Hudson River into Manhattan, both have continuous pumping systems and dedicated drainage rooms. They've never flooded since they opened in 1927 and 1937, respectively. Every parking garage, built underground in any major city, there's a sump pump at the lowest point. Every basement in every flood-prone city. Same principle, smaller scale. The Channel Tunnel between England and France, constant pumping along its 31-mile length. Underground military bunkers, deep mines, every metro system in Bangkok, Singapore, London, all of them are running continuous water removal somewhere in the structure, even the lower levels of skyscrapers. The basements of buildings like One World Trade Center pump out groundwater every day, all year, just to keep the foundation rooms dry. Every one of these structures is doing the same thing your subway does, accepting that water is going to get in, designing the system to push it back out faster than it arrives. Now for the honest trade-off. The pumping never stops, which means the energy bill never stops. The MTA spends a substantial part of its operating budget just on the electricity required to move that water. The system is also vulnerable to power outages. During Sandy, when electrical power to the subway was cut, the pumps stopped. That's when the real damage happened. Backup generators are expensive, and getting them to every pump room in a 472-station system is still an unfinished project. The other honest concern is climate change. Sea levels around New York are projected to rise between 8 and 30 inches by 2050. Storms that used to be once-in-a-century events are projected to happen every 10 to 20 years. The 100-year flood is becoming the 20-year flood. The flex gates and tunnel plugs were designed to handle Sandy. They may not be enough for what's coming. And the system can still fail in unexpected ways. In September 2021, Hurricane Ida didn't even hit New York directly. It came through as a remnant tropical depression. but it dumped so much rain in such a short period that the regular sewer system couldn't handle it. Water backed up through the manhole covers and burst into stations from below. At the 28th Street station on the 1 line, water shot through a manhole cover on the platform like a geyser, drenching commuters waiting for a train. The city welded that manhole cover shut shortly after. So here's where you land. That dry platform you were standing on while the city above turned into a river isn't dry by accident. It's dry because 700 pumps are running somewhere beneath your feet, pushing 13 million gallons of water back out every single day, including the day you noticed nothing at all. It's dry because a fabric and steel barrier engineered from spacesuit material is sitting folded above the entrance you walked through, ready to deploy. It's dry because of one historic failure that taught a 100-year-old system how to be ready for the next one. You've been moving through one of the most aggressively dewatered structures ever built by humans, and you've never once heard a pump turn on. That's not luck. That's a 120-year-old system fighting a battle that began the day the first tunnel was dug, and that has not stopped. Not for a moment, not once, since 1904. If you think subways are weirder than they look, wait until we get into the rivers underneath New York. The actual streams and creeks that used to flow across Manhattan before the city was built, that are still down there, buried under the streets, leaking constantly into the subway tunnels. Because some of the water those pumps are removing tonight isn't from the rain, it's from a creek nobody alive has ever seen.